The second algorithm for the minimum spanning tree problem that we'll discuss is called Prim's algorithm. And again, the idea is pretty simple and it is based on somewhat different mentality here. So with the Kruskal's algorithm, we started with a graph having only nodes and we treated it essentially as a forest consisting of n trivial trees. And then we were merging two trees at a time at every iteration to obtain a single tree in the end. So we started with n trees, then we performed n-1 iterations, and in the end we merged them all into a single tree by adding edges, right? So in a way, you could think of this as destroying a forest. You know, you started with many trees and you got only one in the end. So a somewhat negative connotation.
If this is some kind of practical joke, it's not funny. And I know funny. I'm a clownfish.
But in the case of Prim's algorithm, we can describe it in more positive terms with more positive associations. So in this case, we are essentially growing a tree from scratch. So we start with an arbitrary root vertex S, let's say, and we build on by adding one edge at a time. At every iteration we just have a single tree, but that tree is getting bigger and bigger. We always pick a cheapest edge that connects a tree vertex to a vertex from the outside of the tree and add it to the tree. And then in the end we'll have a tree consisting of n-1 edges, and this will be our optimal minimum weight spanning tree. Alright, so let's again consider the same graph and illustrate our algorithm by applying it to this graph. So let's start with the node 1 as the seed node. And in this case, we actually color the node that we already included in the tree in green. And as a result, we'll have two types of nodes. The green nodes, those that are already included in the tree, and the white nodes that are not included in the tree. And then at every iteration we are going to look at the edges that connect green and white vertices, and we'll mark those edges in yellow, and we'll need to pick a minimum cost edge that is yellow at every iteration and add it to our tree. So it is that simple. So starting with node 1, we see that there are 4 yellow edges that connect this green node to white nodes, and clearly the smallest cost one would be the edge 1, 4. So we are going to include this edge in our tree. So now our tree is a little bit bigger, so now we have 2 nodes and 1 edge, and the total weight of our tree is 6. And adding node 4 created many more yellow arcs here, as you can see. Essentially all arcs connecting a green node with a white node will be colored in yellow, and these are our candidates to be added to the tree next. And of course we are going to pick the smallest weight yellow edge and we'll add it to the tree. So we have 2 edges of weight 7 here, and this is the smallest weight among all the yellow edges that we have. So we are going to include one of these edges in our tree. So we included the edge 3, 4. And as in the case of Kruskal's algorithm, we mark the edge that has both endpoints that belong to the same tree in red. So this edge cannot belong to our tree, right? We'll just mark it in red for convenience. So after we added this edge of cost 7, we see that 3, 6 is the next edge we are adding because it is the cheapest yellow edge. So we are adding this edge. This is going to eliminate now the edge 4, 6 and adds 2 more yellow edges, one of which happens to be the smallest cost edge among all the yellow edges at the moment, and this is the edge we are going to include next into our tree. So we add the edge 6, 8. This creates a couple more yellow edges here connecting 8 to the white vertices. And now we see that we are going back to the cost of 7 and we are going to add the edge for 7 next. So now our tree has 6 nodes and 3 more nodes remain white, right? Obviously now the lightest yellow edge will be 5, 7 of cost 4, so this is going to be the edge that we are going to add next. And there are a couple more white nodes remaining, and there are 2 yellow edges of cost 8, so either of these can be included in the spanning tree first. We add the edge 7, 9, and the final step will be to add this edge 2, 5, and again we obtain the same optimal spanning tree of total weight 51. And you see at many steps we actually have more than one candidate to be included next in our solution, so we essentially break the ties at random, and whatever choice we make, we are guaranteed to obtain an optimal solution in the end. So in some cases you may have alternative optima, but the bottom line is that both Kruskal's and Prim's algorithm guarantee optimality of the solution that they produce. Both of these algorithms belong to the class of algorithms called greedy algorithms, and you can see why they're called greedy, because you're essentially picking the cheapest option you have as you build your solution one step at a time, right? So your greedy strategies are different, but both of them yield the optimal solutions.
Well, I haven't had this much excitement in 200 years.